This is Dr. Lewis going through another molecular orbital energy diagram, and this is for the trickier one, which is the pi orbitals of an aromatic compound. So remember, for the aromatic compounds it makes it a lot easier to first use the frost circle. So we draw a circle. I'll tell you what, we'll draw a hexagon first. Remember, you have to draw whatever shape it is on the apex, so the point always has to be at the bottom, and then we can draw a circle around it. And there's a line through the middle, and that's the atomic orbital. So anything below that would be lower in energy, bonding, related to the atomic relative to the atomic orbitals, and anything above it would be antibonding. So each vertex is an orbital. And there are, remember, 2, 4, 6 pi electrons. So in benzene we fill them up like that. So that would be quite easy, wouldn't it? But so that's the relative distribution of the molecular orbitals, but then we've got to give each molecular orbital in turn. But that's how the picture is going to look. We're going to have a lowest energy one, 2 degenerate ones, as in the same energy, then 2 anti-bonding ones of the same energy, and again 1 anti-bonding one at the top. So we can draw hexagons in a picture, the same sort of layout as that, hopefully with enough room. Alright, and there's our line between bonding and anti-bonding. So the first one's always easy, there's no nodes, so we can just draw lots of p orbitals and every orbital on the top will have the same phase, so it's bonding and those electrons are able to go whiz around and around, delocalized. The next one has 1 node, and so there's 2 degenerate ones, so obviously they're not going to look the same, but they'll have the same energy. So one we can create by putting a node across the middle. So then we have one that looks very much like the bottom one, but now the top half and the bottom half, there is a node. So there's an anti-bonding interaction between that pair and that pair, but there's bonding between those, and those. So there's 1, 2, 3, 4 bonding, 2 anti-bonding, so there's altogether 2 bonding interactions. So that's why it's still lower in energy than the atomic orbital energy. So the other node, or the other degenerate orbital, we place the node through 2 vertices, and now that's going to be bonding on this side, and then they're going to have opposite phase on the other side, but obviously it's still bonding on that side. So now we've got 2 bonding, but there's no anti-bonding because they're too far apart to be anti-bonding. So that's why they're the same energy, even though they look very different. Now the one above that, we've got 2 nodes. So we can have a node through there and a node through there, and that will give us a picture like that, where that's and there's a node there, so that phase is going to be opposite to that one, and this is going to be again opposite to that one. Have I got that right? Yeah. So that's that one. And the next one is going to have 2 nodes, but it's going to be like this. So we now have some bonding interactions, so we could put one in. That's a bonding one. But this one here is anti-bonding. That one there is anti-bonding. This one's bonding. And hopefully we'll get round to the other side and still be okay, the lobes. So now the bottom one is right. So again, that's right. So that's anti-bonding. So it's bonding, anti-bonding, anti-bonding, bonding. And the very top one has got 3 nodes, so that's easiest one of all. So basically it goes again alternately, sort of out of phase on every atom. So if I start with that one, I go down and back up, and down and back up, and down. So there's anti-bonding interactions 1, 2, 3, 4, 5, 6. So it's very 1, 2, yeah, very definitely anti-bonding. If we compare that one with that one, there are 1, 2 anti-bonding interactions, and here there are 1, 2 bonding, and 1, 2, 3, 4 anti-bonding. So remember, 2 of the anti-bonds get cancelled out, so they are the same energy, even though they look very different. Right, so we can now stick in our electrons. And a benzene ring has 6, which means we start from the bottom. That would be a good idea. 2, 4, 6. So they all lie in bonding orbitals. So these ones are the HOMO, and the ones above that are the LUMO. And to finish it off, I'll just draw a little energy thing there. And that's it. Definitely a lot more to do than for a linear one, but it does, if you follow the rules, you don't always have to know it off by heart. You can work it out without panicking. Okay.